Up until now, we've talked about momentum at a specific moment in time. Sometimes it was of a car driving down the road. The momentum of the car right now as the car drives down the road. Sometimes we had a ball dropping from the top of a building, and we wanted to find the momentum at the end of the fall. Or, for that matter, we could have found it in the middle of the fall. The bottom line is momentum has to be found at one specific moment in time, and therefore you need one specific velocity that corresponds to that one specific moment in time. But how do we quantify that change in momentum? When a car slows down at a stop sign, it experiences a change in momentum. Or when the ball falls down towards the ground, it experiences a change in momentum. We haven't learned to quantify that yet. We've just learned to quantify the momentum at one specific moment. Today, we're going to talk about impulse. Impulse is defined as the change in momentum. The momentum gained or the momentum lost by something. Momentum lost by that car as it slowed down at the stop sign, or gained by that ball as it fell towards the ground from the top of the building. The change in the momentum experienced by the object, not the momentum at one specific moment in time. Of course, it's a vector quantity. Because momentum is a vector, anything that's a change in a vector is going to be a vector itself. So there is a direction associated with it. The change in momentum is to the left. The gain in momentum is to the right. The gain in momentum is to the left. So on. Now we're going to derive an equation for impulse here, this change in momentum. But we're going to do it from something that you learned last year, Newton's second law. Does anybody remember Newton's second law from Physics 20? Remember the first law? An object at rest stays at rest. An object in motion stays in motion at a constant speed, straight line until acted upon by an unbalanced force. Third law was basically for every action there's an equal and opposite reaction. What's the second law? I'll give you a hint. We can describe it pretty easily by an equation, by a relatively simple equation. Newton's second law says the acceleration is proportional to the force and inversely proportional to the mass. In other words, if we rearrange it, F is equal to m times a. So let's write that down. That's where we're going to start here. F is equal to m times a. But you know what? We know that a is also equal to delta v over delta t. Is that okay to do that? Is that legitimate? A legitimate step there? All we're doing is subbing in delta v over delta t. And since a is equal to that, then I think that's okay to do. Let's go to our next step now and just rearrange this. Let's take the t up by multiplying. We end up getting f times delta t is equal to m times delta v. Now, a question for you. What's m times v equal to? Not m times delta v. What's m times v equal to? We should all know this. We better. M times v is what? Momentum. Right. Okay, if m times v is momentum, then m times change in v, so we got there right there, right, is equal to what? mv is momentum, m change in v is the change in momentum. In other words, it's the impulse. M times delta v is the impulse. But look what just happened. We got an equation, m times delta v, which is a pretty intuitive equation for impulse, right? M times the change in velocity would be equal to the change in momentum. But we've also discovered that impulse is equal to f times t. But that should make sense to us as well. How do you change the momentum of something? If a car is slowing down at a stop sign, how do you do that? How do you decrease its momentum? How do you increase the momentum of the ball as it falls towards the ground? Well, you apply a force. But it's not good enough just to have a force. That force needs to be applied over a certain amount of time. So the bigger the force you apply, the bigger the impulse. The bigger the change in momentum is going to be. The longer you apply that force, the longer the ball falls, the longer the car stops, okay, the bigger the change in momentum is going to be. Does that make sense? Now, one little thing here. On your data sheet, if you look in the bottom left-hand corner of your data sheet under energy and momentum, you're going to see this equation. F times delta t is equal to m times delta v. It doesn't mention the word impulse there at all. We're going to just have to remember that that equation represents impulse. And if you're ever asked to solve for impulse, use either F times t or m times delta v to find that. If you want to make yourself a little note on that data sheet right now, that's fine. Go ahead and do that. Just remember on your diploma exam and on your unit test coming up, you're just going to have to remember that yourself. All right, in a little while, we're going to do some problems with impulse, but I want to identify first when we're going to use impulse to solve those problems. In other words, what problems we're going to attack with impulse. There's three things here. And the first one is pretty obvious, I think. Question, good, ladies? We're just going to use the word. We're just going to use the word. That's a good question. We're just going to use the word. But sometimes you'll actually see, not in physics 30, but down the road, if you ever take physics, sometimes you'll actually see the letter J. But since it doesn't actually appear anywhere on our data sheet, I've just chosen to use the word as opposed to some crazy symbol that doesn't really make much sense. Yep. What you don't want to do is get caught up in putting an I, because I stands for something else in physics, electric current, which we're going to see in a few months. So when are we going to do this? What kind of problems are we going to attack using the concept of impulse? Well, the first one is really, really obvious. If you're asked to solve for velocity, you're going to use a velocity equation. If you're asked to solve for force, you're going to use a force equation. If you're asked to solve for impulse, you're going to use impulse, right? Like, you know, a grade sixer could figure that one out. If you're asked to solve for impulse, use the equation that's for impulse. So that's the easy one. You're never going to have a problem with that one, I don't think. The second one is a little less obvious, but still not bad. Impulse is defined as the change in momentum. So whenever you've got a problem involving a change in momentum, it might say, what's the momentum gained by the object as it speeds up towards the ground? What's the momentum lost by the car as it slows down at the stop sign? If it refers to a change in momentum, a momentum gain, a momentum lost, then let's do impulse. Let's use this equation. And the third one, this is the one that's the least intuitive of them all. Remember we said just a second ago, you need two things to have an impulse. You need two things in order to cause a change in momentum. You need a force, and you need that force to act over a certain amount of time. Whenever you see a force and a time in the same problem, let's do impulse. What's a little anti-intuitive about that is that a lot of these questions involving force and time that you're going to use impulse for don't even mention the word impulse, don't even mention the word momentum. It might say a force of 10,000 newtons is applied on this 2,000 kilogram car for 60 seconds. What's its final velocity? There's nothing that intuitively directs us toward impulse on that, right? But since there's a force over time, the momentum of the car will change. Therefore, there is an impulse. Therefore, we can use this to solve the problem. And you're going to see how in just a few minutes here. So three things. When you're asked for impulse, when you've got a change in momentum, momentum gain or momentum lost, and then finally, this is the tricky one, when you have a force and a time in the same problem. Now, having said that, there is rarely a case when you need to use impulse. There is usually another way to solve the problem. Impulse is just sometimes a more efficient way to solve the problem, and a more versatile way sometimes to solve the problem. In the end, impulse, F times delta t is equal to m times delta v, really is just Newton's second law. It's another form of Newton's second law. So in most cases, if you can solve it with impulse, you could also solve it with this equation in combination with one or more equations. Okay? But listen, if we've got one equation, everything together, then why would we solve it with, a couple of different equations substituted into one another? Okay? But in the end, if you're stuck, go back to the old physics 21. Let's take a look at an example on page 458 here. It's a great question because it deals with the quantitative impulse, i.e. the numbers, when we use impulse and how we do it. But it also deals with some of the qualitative implications of impulse that we'll talk about in more detail in a little while here. Give you a chance to read this question, okay? See if anything jumps out at you. If there's any words that don't make any sense. Is there anything you can kind of draw from this question as to what we should do with it? All right, anything that doesn't make sense there? We're going to see sometimes questions where you've got an entire page of information to answer 3 or 4 questions, and sometimes that page of information is going to have some context that is so foreign to you that there's going to be word upon word upon word that just isn't going to make any sense to you. Okay? Usually they're not physics words. Usually they're kind of outside words that doesn't really matter if you know what they mean, but okay, we still want to be able to understand the entire question as best as we can here. To improve the safety of motorists, modern cars are built so that the front end crumples upon impact. So what that means basically is when this car crashes into the wall, the front end gets destroyed. The front end gets a lot smaller. It compresses, right? And that's for a safety feature. That's a good thing. Okay, older cars didn't do that very much, and car stood up better to a crash, but you didn't stand up better to a crash, because in the end, all the energy was transferred to you instead of the car itself. A 1,200 kilogram car is traveling at a constant velocity of 8 meters per second. It hits an immovable wall and comes to a complete stop in 0.25 seconds. So it was going at a constant velocity, but then it's stopping. We want to find the impulse provided to the car. We want to find the average force exerted on the car, and then we want to do something else with a different stopping time. So let's deal with A and B first, and then we'll take a look at C after we've kind of internalized A and B here. Let's write down some givens. Here's something, 1,200 kilogram car. What's that? All right? All right? Good. Let's get off the hook on the easy ones, right? Because sometimes it gets a little bit harder later on. That's the ticket, right? Raise your hand early. Okay, raise your hand early. Get off the hook with the easy givens. Then when the hard ones come along, I'm not going to call on you, right? Call on somebody else. It's traveling at 8 meters per second. That's something. Tell me what that is. It's a little bit trickier. 8 meters per second. Doesn't sound tricky, but really? Is it V? Not quite. Almost though. V. Let's put a little subscript in there. Which subscript do we want to put below the V? It says a constant velocity, right? But in this problem, we care about the stopping of the car. So when the car stops, 8 meters per second would correspond to VI, the initial velocity. Good. This is time, right? This one's easy enough. I'll do that one. Anything else? If we read between the lines here, do we have anything else? Ken? Good. Good. The F is 0 meters per second. Okay, we have to catch that. It comes to a stop. It doesn't write down the number, 0 meters per second, but it tells us in a little bit of a roundabout way that the F is equal to 0. We want to find the impulse provided to the car. So let's write down the word impulse. Or, you know what we could do? Somebody asked me for the symbol for impulse. Okay, you know what we could do? We could just say impulse is delta P. Okay, that's a pretty intuitive thing to write down as well, right? Not J. Shorter than writing the word impulse. But if you want to write that word out too, that's fine, because that's what I often do. All right, what's the impulse provided to the car? We know that impulse is equal to either F times T or M times delta V. Either one. Which one seems to be the most useful here? Which part of the equation? The first part, F times T, or M times delta V? Yeah, let's try M times delta V. We know what T is, but we don't know what F is. So that's not going to be very helpful to me right now. But I do know what M is. I do know what VF is. I do know what VI is. So M times delta V works here. Let's say 1,200 kilograms times VF minus VI, 0 minus 8 meters per second. Okay, we do the math there. And I believe that works out to be a negative 9,600 or negative 9.6 times 10 to the 3. And what would the units for that be again? Momentum. Mass times velocity. Impulse, same units. Kilograms, meters per second. Hey, quick question here. We got a negative value. What does that mean? What's the implication of the negative here? You can think of it in one of two ways. Simon? Well, it's traveling to the east, so the impulse is to the west. Okay? It's moving to the east, but the impulse would be to the west. Okay? Or the other way you can think of it, Devin, it's a loss of momentum. You're moving to the east, you lose momentum as you're moving to the east. What's the average net force exerted on the car? Question B. The average net force. Like I said a minute ago, if you're stuck, you can go back to F is equal to M times A. That's a force. Get A, plug it into there, solve for force. That'll work. But there's a more efficient way of doing B now. We want to find the average net force. Let's say delta P is equal to F times delta T. We already got delta P, the impulse. We just found it, negative 9.6. We know what T is. Delta P is neg 9.6 times 10 to the 3. Delta T is 0.25 seconds. Divide those two numbers, and we should get neg 3.84 times 10 to the 4, I believe that is. Is that right? Newtons. Which means it's negative. Listen, if you're moving to the east, which way does the force need to be if it's going to stop you? To the west. That's why we get a negative value there. Simon, is that the right answer? Good. Now, question C. Question C. For the same impulse. I like it when I see that word same. Why? Well, it tells me what to do right away. For the same whatever, for the same impulse in this case. It tells me in question C that the impulse in question C is neg 9.6 times 10 to the 3. It's telling me what the impulse is. It's the same thing as it was. Now we got a time here of 0.40 seconds, or 0.040 seconds. We're going to find the force. It's the same question pretty much as question B was, except that in this case, we got a different time. Delta P over delta T. What does that one work out to be? You're 240,000 or negative 2.4 times 10 to the 5 newtons. What do you notice about these two forces? Take a look at the numbers. What do you notice about them? Clearly, they're not the same value. Are they in the same direction? Yes. I mean, in both cases, we're stopping a car that's moving to the east. In both cases, the force must be to the west. What about the values of them? Are they the same value? No. Which one's bigger? Uh, 0.25 seconds? No, the other one, right? 0.04 seconds. So So question C has the bigger force, right? Right? Almost 10 times bigger than the force in question B, almost. Why is it bigger? Here's the thing, and we're going to talk about this later on after you do some problems here, but when an object stops, it will experience the same impulse no matter what. When a car stops, you're traveling down the highway at 100 kilometers per hour. I don't care if you're driving to Edmonton or you're driving to Dairy Queen. Well, I do care if you're driving to Dairy Queen because you shouldn't be going 100 going to Dairy Queen because the speed of it's only like 50. But if you're driving to Edmonton or you're driving somewhere on the highway just close by, I don't care how far you're driving. I don't care how you get that. In the end, I can tell you right now what your impulse is going to be because I know what your mass is and I know what your change in velocity is. It's 0 minus 100 kilometers per hour. I know what your impulse is going to be no matter how you stop. I don't care whether you come to a gradual stop at a stop sign, 300 kilometers away. I don't care if you slam on the brakes 3 kilometers away. Your impulse will be the same. Your impulse is predetermined, we say. It's going to be the same no matter what. What if, God forbid, you're driving at 100 kilometers per hour and you crash into a concrete wall? Well, your impulse is still going to be the same. What isn't going to be the same? Force. And why isn't it going to be the same? Well, because when you're coming to a gradual stop at a stop sign, it takes you a long time to stop. When you come to a crashing stop into a concrete wall, it takes you just a moment to stop, just a brief second to stop. The longer it takes you to stop, the bigger the stopping time, the smaller the force. Okay? That's why we want to gradually stop instead of crashing into a concrete wall. The impulse will be the same, but the force won't be. And it's force that hurts you, not impulse. That's why, anybody ever been in an accident where the airbag has gone off? Yes? Driving? Okay. So you were in passenger seat, airbag went off in the passenger seat. Okay. That's why we have airbags, right? You're coming to a crashing stop. Your stopping time is very, very quick. Well, what an airbag does is just increases that stopping time just a little bit, of your head at least, right? Which is the most important part of your body, right? Increases the stopping time just a little bit, decreases the force. What happened here in question C? We decreased the stopping time. What did it do? It increased the force. Most times, we want to decrease the force, unless we want to break something, in which case we would want to lessen the stopping time to increase the force, right? We'll talk more about that a little bit later on after you've worked on a couple questions here. Questions I want you to work on right now, page 458. Give you about 10 minutes and see what you can do with it. All right, everyone, have a look up here. I want to take a look at question number 2. We've all read the question. The dog team pulls a 400-kilogram sled that has begun to slide backwards. In 4.2 seconds, the velocity of the sled changes from 0.2 backwards to 1.8 forwards. I'll tell you what, one thing that I would like to do, and one thing that I would like you to do for the rest of this year, is when you see something like this, backwards and forwards, in the same question, circle it in red, or highlight it in pink, or just draw attention to it somehow, because that is such an easy thing to miss when we go to do our calculation. Forward, backward. If you got 2 different directions, something's got to be negative. So draw attention to that. Okay, we may very well know how to solve this problem, but if we miss a negative sign, we're still going to get the wrong answer. And I know that at least some of you have done that in this question, probably lots of you. Here's my mass. Here's my time. What's this? What's this 0.200 meters per second? VI. But we're going to make it negative, right? So I'm actually going to write that in, negative 0.200 meters per second. Again, just to remind me when I go to do the calculation that I've got to make it negative. Okay. I remember to make it negative now as I'm going through my givens here because I circled it in red. But I still want to draw attention to that by putting the negative right there. This is going to be VF. It's a positive because it's forward. want to find the average net force. We want to find the force here, so let's use that. This is an impulse problem. It can be at least an impulse problem. Why? Which one of those three criteria tell us that this could be impulse? Does it ask me for impulse? No. Does it talk about the change in momentum? There is a change in momentum, but it doesn't talk about it, right? It doesn't mention momentum gained or lost, just says calculate the force. All right, so option number 2 doesn't work. What about the third one? Is there a force and a time in this question? Okay, we got to spot that, right? We got to see that right away. Even 3 months from now, we've got to notice when there's a force and a time in the same question telling us that it's going to be impulse. We know that impulse is equal to F times delta T, but we also know that it's equal to M times delta V. Let's use the M times delta V here. Because we know what M and we know what delta V is. But wait a sec, that doesn't give us force. Let's try this. Let's try impulse is equal to F times T, but also equal to M times delta V. Let's try the equation as it appears on my data sheet. Force becomes equal to M delta V over delta T, or 400 times, now be careful here, delta V is VF minus VI, 1.80 minus 0.2, right? Over the time of 4.2 seconds, right? Brian, when we do that, we don't get the right answer, right? What's wrong? Right, I got to make it negative 0.2. So it becomes 400 times 2 divided by 4.2, which gives me 190 newtons. And that's going to be a positive number, which means it's forwards, if I define forwards as positive. All right? How many people got that? How many people forgot the negative on the 0.2 the first time around? Okay. It's 3 of you, 3 out of 12. It's a quarter of you, and it's probably more than that. Just some people are probably afraid to put up their hand for it. So it's a common mistake. What do you think would happen if this is a multiple choice question? The correct option would be 190. One of the incorrect options would be whatever you get when you forget to make that negative, right? Don't make that mistake, because they're gonna know that. They're gonna know that you'll make that mistake, and they're gonna put that as an option. All right, I want to take a look at a couple multiple choice questions here. All right, I've asked you to take a look at this question and then submit the responses. I've taken a look at the answers that you've gotten here. They're split between A and B. 23% of you said option A. 77% of you said option B. Let's hope B is right. Okay, but let's take a look at why A is wrong, if in fact it is. It says, in an automobile collision, the severity of the injury to the driver can be reduced by an airbag. We talked about that a little bit, right? Increases the stopping time, decreases the force. The car initially traveling at 100 kilometers per hour, hey, I want to draw attention to this. That's something that's not normal. Okay, we don't want kilometers per hour. That's an easy place to make a mistake. I might forget to convert that to meters per second later on. I spotted it. I'm going to circle it in red to draw attention to it. Stops a 62 kilogram driver in 90 milliseconds. Same thing right there. I want to draw attention to that one as well, just so that I don't forget when I go to do my calculation. The magnitude of the average force exerted by the airbag on the driver is a what? What kind of problem is it? Probably impulse, right? Because that's what we're doing right now. Why? What tells us that it's impulse, besides the fact that we've spent all day on impulse? There's a change in velocity? Okay, there is. Okay, that's not one of the 3 criteria, though. In the end, I'll tell you what, though, Ken. In the end, if there's a change in velocity, there is an impulse. But when you see a change in velocity, it's not necessarily enough information to use impulse. That's what I'm saying there. Okay? There's something here that tells me that we have enough information to use impulse. And what is it, Tom? Right. We got a force and a time in the same question. Okay, that's enough to tell us, go ahead, do impulse. All right, we know the impulse equation says F times delta T is equal to M times delta V. We're looking for force. We got the time, we got the mass, and we got delta V. Good, good. So let's just say F is equal to m times delta V. Let's divide the T on the right-hand side. We get 62 kilograms. Let's say 100 minus 0, or be 0 minus 100, right? Or it would be 0 minus 27.77, right? Because it's got to be converted to meters per second. What's the conversion again from kilometers per hour to meters per second? Yep. Good, good. The time here is 90 milliseconds. Now, somebody asked me, how do you convert milliseconds to seconds? It's on your data sheet. In the middle, the very middle section of your data sheet, it has all these metric prefixes. Milli is one of them. It says a milli is 10 to the minus 3. So let's not move the decimal place. That's just confusing. A milli is 10 to the minus 3. 90 milliseconds is 90 times 10 to the minus 3 seconds. We do the math there. I think we do end up getting negative 1.9 times 10 to the 4 newtons. But since they only asked me for the magnitude of it, positive is okay. Now, what happened with option A? 23% of you said option A. Was that you forgot to convert kilometers per hour to meters per second? Is that what you got? Yeah. So, obviously, we make a silly mistake like that. Okay, it's going to happen. We all make those mistakes. But they're going to count on that, right? And they're going to trick us into putting option A there. Tom?
So I thought it was a trick, but there wasn't an option for that to be above. But I got 1.9 times 10 to the 3.
Okay. 1.9 times 10 to the 3. Now, they never give you a trick like that. Never give you a trick like that. So what's happened is you've probably converted something wrong. You might have put 9 times 10 to the minus 3 or something like that instead of 90 times 10 to the minus 3. Or if you move the decimal place over, you might have moved it over wrong. So be careful about that. You got lucky on that one because it wasn't an option, right? Just be careful. Okay, this one is a numerical response question. I'm going to ask you to submit this one, please, as numerical response number 1 on that same form. Okay, we got good news here. Most of the responses are the same here, okay, and that response is 1.94 Newton seconds, and that's the correct answer here. What tells us this one is impulse? Honestly, as I read through this question, this struck me in the beginning, 130 newtons. I thought, oh, that's going to be impulse. It's going to be F times T. But then I realized there's not actually a time here. It doesn't mention time at all. So that's not actually very helpful, the 194 newtons. Down here I see that we're actually asked for impulse. Well, clearly, it's going to be an impulse question. But not because we see a force, but rather because we're asked for impulse. Delta P is equal to F times T, but it's also equal to M times delta V. Mass is 20.6 times 10 to the minus 3. 20.6 grams. Probably should have circled the grams just to remind me to convert that to kilograms. Change in velocity, 94 minus 0. And when we do that, we end up getting the 1.94 Newton seconds or 1.94 kilograms meters per second, either way you want to express that. Okay? One more multiple choice question here. One more. Let's take a look at multiple choice number 4 now. That's also in your multiple choice review sheet. And submit that one as multiple choice number 1, please. Good time. All right, let's take a look at this one here. The SI units for impulse. We read the question, something actually, I always tell you guys when you read a question, is there anything that doesn't make sense to you? Any words that are kind of foreign to you that don't make sense? This one kind of is. The SI. What does SI stand for? System International. It's the metric system, right? So in other words, what are the metric units for impulse? The standard metric units for impulse. We could go F times T gives us Newton seconds. We could go M times delta V. That would be kilograms meters per second. Are either one of those there? Answer would be B, right? Good? All right. Perfect timing. Perfect timing. Just in time to give you your homework. Your homework is worksheet number 2. The good news is there's 9 questions on that page, and I'm not going to make you do all of them tonight. I'm only going to make you do 8 of them tonight. So get those done for tomorrow, guys, and we'll take a peek at them then. All right, that's it for today.